Okay. 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 Oh, hi. I was just looking at my deck of Uno cards here, and I noticed that there's quite a few wilds in this deck. And I wanted to know, one of my friend's strategies when we were growing up and playing Uno a lot was he liked to hold on to a wild card until the very end, so that no matter what anyone played, he would be able to play it. And so that kind of got me thinking about Uno and the types of ways that you could maybe draw some cards out of an Uno deck. And so what I did was I went through and I pulled out some wild cards. I pulled out 3 of the big daddies, the draw 4 wilds, and I pulled out 2 of the regular wild cards. And what I want to try to do is I want to try to see how many ways there are for me to put these 5 cards in order. And so what I've got down here is I've got a piece of paper set up and a column for possible permutations. And I want you guys to kind of help me sort of count the number of ways I can arrange these objects so that we can figure out how many ways there would be to arrange these 5 cards that just happen to be all wild cards. Okay? So come on, let's see what we can do. Okay? So we've got these 5 wild cards here. So what I'm going to do is here, I guess I could just stack them up a little bit. Okay? So I've got them arranged in this way. So that's going to be one way that we can arrange them. Alright? And so I'm just going to mix up the order a little bit. What if I put these 2 first? Okay. And then those 3. Well, that's another way. Okay. So that's going to be 2. And then what if I took this one and I switched the order here? Okay, so that's another way, I guess. Well, it looks like this could take a little bit, so what I'm going to do is I'm going to maybe speed up the motion a little bit so we can see some more of the possibilities of arrangements, and you can kind of count along with me. Okay, so here we go. This is taking forever. Aside from the fact that I'm holding the camera, this has taken so long to figure out all of these permutations. Surely there has to be an easier way. Let's see what we can find in our lesson today. Today we're going to talk about permutations of indistinguishable objects. Like we had in our little intro, the draw 4s and the wilds were indistinguishable because this draw 4 looks like this draw 4. They look the same. That's what makes them indistinguishable. And so when we talk about permutations, really what we're talking about, things that don't matter which is which. That's indistinguishable. So it doesn't matter if it's one draw 4 or the other. Let's consider some letters for an example. If we have 3 B's and 2 C's, let's assume that the letters are distinct. Okay, so let's say that they did matter. Let's say we knew which one was which. So we're saying we have 5 distinct possibilities. And so what we would do is we would say, well, we have 5 bins that we could possibly put them in because we have 5 total letters. So it's going to be 5 times 4 times 3 times 2 times 1. Nice and easy. 120 permutations. But the problem comes in when we have letters and numbers that aren't distinguished from one another, because BBB is the same as BBB, regardless of which one it is. And so what we are going to do is we're going to look at the problems that this can cause. So if we pick the order of the 5 letters, we don't necessarily know how many ways there are. But we do know how many ways there would be if they were distinct. There are 120 ways. Okay? If the letters are distinct like this, the possibilities look something along these lines. The ways. So we could have B1, B2, B3, C1, C2, or we could have B2, B1, B3, C1, C2. But then again, we could have B1, B2, B3, C2, C1. Or we could have B2, B1, B3, C2, C1. Or we could have B2, B3, B1, C1, C2. Or we could have B2, B3, B1, C2, C1. Or we could have B3, B2, B1, C1, C2. Or we could have B3, B2, B1, C2, C1. Or we could have B3, B1, B2, C1, C2, B3, B1, B2, C2, C1. Ugh, it's all so much. Okay, so if we think about the number of ways there are to pick just the B's, okay? To pick just the B's. There's 3 possible B's. So that means we have 3 distinct bins to put them in, right? So 3 times 2 times 1. 6 ways for just the B's. But what does that mean for our C's? Well, for just the C's, we have 2 possible. So we have 1, 2. So there's 2 possible ways to pick the B's. Think about what this means. What we're basically saying is, regardless of how you pick the B's, whether it's B1, B2, B3, or B3, B2, B1, if they weren't distinguished, if they didn't have the 1, 2, 3 on them, wouldn't that be the same? It's like saying, I picked this draw 4, I picked this draw 4, and I picked this draw 4. Well, if I mix them around, which is which? We don't know. That's the point. We're saying to pick these 3, there's 6 different ways, because in the first slot, to pick the first card, there's 3 possibilities. Then there's times 2 times 1. There's 6 ways to pick just these 3 cards that all yield the same result, right? Because whether they're in this order, or this order, or this order, aren't they still the same 3 cards? And so what we are going to do is we are going to take all of this out. And we're going to consider the fact that 120 ways and B, 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 C, C is the same as B, 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 C, C. So what does this mean for us? It means, how do we account for repeats? How do we account for the fact that this is the same as this? Is the same as this? We say something like this. Total possibilities. Five factorial, because there's 5 separate slots. And we divide by the possibilities for B times the possibilities for C, divided by 3 factorial times 2 factorial. Okay? So this means it's going to be 120 divided by 6 times 2 equals 120 divided by 12 equals 10 ways. Okay? If you didn't catch that the first time around, maybe write yourself a note. but we're going to take the total number of possibilities and divide by the number of indistinguishable objects of each type. That means this: the number of permutations of n objects, in our case it was 5, where r is the number of types of objects and k is a set of identical objects, looks like this: n factorial divided by k okay? We are dividing by the number of indistinguishable objects of each type, okay? Let's do an example because sometimes the math part of it can get in the way of our understanding, okay? So let's look at it. If we have 7 identical dice, okay, we're going to find the number of ways to roll 2 4s and a 5 and 4 6s. This should be 1 5. Typo. So, out of 7 dice, we want 4, 4, 5, 6, 6, 6, 6. We want that. But it doesn't matter whether you roll the first die as a 6, the third die as a 6, or 4 straight as 6s. So we're going to take out all those possibilities. And so what we're going to have is, we are going to have 7 factorial divided by, now there's 2 objects here, there's 1 here, and there's 4. So this is going to be 4 factorial possibilities. This is going to be 2 factorial possibilities. Okay, so we're going to divide 7 factorial by 2 factorial, 1 factorial, 4 factorial. This takes out the fact that 4 and then 4 is the same as 4 and then 4. Okay, so when we actually do this, we get that this is equal to 105 permutations. Take the total number and divide it by the amount of repeats of each type. Okay? Let's consider another example. In this example, 8 coins are stacked. 3 pennies, 2 nickels, and 3 dimes are placed in this stack. We're going to say that there's no restrictions. This means that all of the objects, it doesn't matter where they are. So a dime, then a dime, then a dime is the same as any order of the dimes. So we don't have to take out that other piece of the equation. We don't have to take out the repeats. And so what we're going to say is there's 8 possible slots, so it's going to be 8 factorial. That's if it doesn't matter if three dimes go in a row, or you put the dimes in a different order, or if you put them in a different order, it doesn't matter. No restrictions means you don't have to take out the repeats. But the problem comes in when we try to say something like the dimes must be stacked together. And so if we look at a stack of coins that has this certain restriction, there are 8 places on that stack. 2, 3, 4, 5, 6, 7, 8. And what we're saying is these 3 have to be stacked together. So it doesn't matter whether they're at the bottom of the stack or the top of the stack or the middle of the stack. We're saying those 3 have to be together. But remember, within those 2 separate stacks now, we have one stack, which is the blue, that has the 3 dimes in it. And there's this other stack of 1, 2, 3, 4, 5 coins. Okay? So these are the dimes. These are other coins. If we consider the fact that there's possibilities for each of these 2 stacks, we have another whole separate problem. And so what we are considering is this. I'm going to a new slide. If we have that set of dimes that has 1, 2, 3 coins in it, these are a set with a distinct number of possibilities. The number of possible stacks equals 3 factorial, right? Because if they're 1, 2, 3, or 3, 2, 1, or 2, 3, 1, the number of possible stacks would be 3. Let's look at our other stack. If we have this stack of 1, 2, 3, 4, 5 coins, and we look at the number of possibilities, what are we looking at? If we're saying that the number of possibilities is based on these coins being in a certain order, we have to account for the fact that there are a number of ways to do this. Okay? And so what we have to do is the same thing that we did before. Remember, in this stack, there are 3 pennies and 2 nickels. Okay? 3 pennies, 2 nickels. Okay? So, the number of possible ways would be 5 factorial. But we have to take out the repeat. So we have to take out the fact that the 3 pennies could be in a different order. So, we're going to divide by 3 factorial, 2 factorial, because this is the repeat of pennies. This is the repeat of nickels. And so what we're going to do is we're going to say the total possibilities is going to look like this. We take the number of dime stacks times the number of other stacks, which is going to be equal to 3 factorial times 5 factorial over 3 factorial, 2 factorial, which is going to leave us with a grand total of 60 ways. Okay? That's what we're looking at right now, guys. We have a total of 60 ways to stack these when we account for the first stack of dimes and the stack of the other 5 coins. You're probably going to have questions on that one, so make sure you write them down in the margin, and we'll see you next time.